we're going to be balancing chemical equations, but before we begin to do so, let's take a look at some of the other things you might see written in the actual equation itself. Like, for instance, down here, you see this parentheses with the S, parentheses with the G. These are symbol notes that you might see in the balanced reactions, and they tell you little information about the particular compounds or the elements that are going to be in the reaction. So the symbol with the little S in parentheses is going to indicate that that compound or element is a solid. So that would be a solid. That would be in the solid phase or state of matter. If you're using states of matter, phases of matter, it would be a solid. The L, of course, you could probably predict now, the L is going to represent the liquid phase. And last but not least, of course, the G, or like for instance here, next to oxygen, O2, that's going to indicate to us that it is in gaseous phase, or it's going to be a gas. Now, probably some of you have seen AQ, the symbol AQ, or understand what AQ might possibly be. AQ is a representation for when certain substances are dissolved in water. They're aqueous. That's what that word means. It's aqueous. The symbol is for aqueous. So a particular salt or a particular substance, a solute has been dissolved in a solvent, water being the solvent, then it is going to have the AQ next to it, so you know it's a solution. Solution that has water as the solvent. This means dissolved in water. Now for the arrow symbol. The arrow symbol actually can be stated in a phrase where it would say the word yield. Yield just means produces. It is the, you have the reactants on the left side of the arrow, the products on the right side of the arrow. So it yields this product, or it produces this product. So when you see that arrow sign, a lot of times it's written as a yield or produces, and you're producing that particular substance on the right side of the arrow, which is going to be the product. Now, if you see above an arrow a triangle like that, or you see the word heat written above the arrow like so, that just means in order for the reaction to occur, it requires energy. So you must give it energy, you must put it on the hot plate, heat it up, or under the Bunsen burner, you need to provide some energy to get the reaction started. Now over here for some other symbols, sometimes used in balanced equations. Sometimes you might see an arrow pointing upward, which is also referring to something in the gaseous phase, like the arrow's pointing up like it's floating away. So if you see an arrow up next to something, that means it's a gas. If you see an element or a compound above the arrow, like sometimes, for instance, you might see an arrow like this with Ki above it, which is potassium iodide, or you might see something above it like with Ni, meaning nickel was added. If you see something like that, that follows this statement right here. Element or compound above the arrow means a catalyst was added to speed up the chemical reaction. So if you see it written like that or written like that with this, either a compound or an element above the arrow, that just means a catalyst was added. Like so, right here, this word catalyst. Now, the last thing up here that you might see as a symbol up here means arrow down. and arrow down is actually referring to something called a precipitate. A precipitate precipitates form a solid crystal that falls to the bottom. So a lot of times in these chemical reactions you'll have two solutions. The two solutions get mixed, and then you'll see solid crystals fall to the bottom, and that would be a precipitate. So let's also add on to that statement that the solid crystal that is, falls to the bottom. And you would see a precipitate form. So these are the symbols that are in the chemical equations that tell you certain little pieces about the phases. Is it using a catalyst? Is it requiring heat? It tells you, on the left side of the arrow are the reactants, on the right side of the arrows are the products. So little tidbits of information there that you will need to pay attention to when you're writing word equations especially, and looking at balancing equations and predicting products that might possibly form in a reaction. So now to balancing the chemical equations. Looking here, there are these lists of helpful hints that you can refer to at any time. If you can't remember the steps as we're working through, and for particular reactions, there are different strategies based off of the type of reaction that you might want to use because it speeds things up and makes it go quicker. So, I'm not going to list these out individually, but I will be working through all of these hints when I do the example problems. So if you can't remember some of the steps, you can always refer back to the hints there. Now, looking at example 1. First thing I should do is identify the type of reaction, which you already have the notes on the front page for. So looking here, we have one compound here, breaking apart into two. A compound, the KCl is a compound, and O2 would be an element. It's an elemental molecule, diatomic, remember O2. So this would be under the heading of decomposition. Now, in order to balance the chemical equation, we do have to understand that we have to follow the law of conservation of matter, also called the law of conservation of mass. And we can write that down at the bottom of the page. Okay, so we have to follow the law of conservation of matter. Which states that matter is neither created nor destroyed. So, matter is never created nor destroyed. It is just altered into new forms. The amount of matter of each element that you start with is how much of the element that you're going to end with. So if you have 5 grams of carbon to begin with, it could be in a compound or be in an element, but you're going to still have 5 grams of that carbon somehow switched around, might be in a new compound, but it still is going to be there. It's going to be the same amount. Whether you start with a certain amount, you're going to end with a certain amount. You may be starting as an element, but in the end it ends up being in a compound. But the amount of matter is not going to change. The mass or the number of atoms, you start out with, if you're going to have 5 atoms of carbon, then you must end with 5 atoms of carbon. It has to be the same amount. So we must follow the law of conservation of matter, nor destroyed. It's neither created nor destroyed. It just is altered and changed in a chemical reaction. Now looking up here to balance, we're going to use a particular method, and I want you to do this on this particular sheet while you're practicing so that you can keep a tally of all of the elements. So we set up a kind of a tic-tac-toe chart. Looks similar to one, but we're going to use it differently. So I put it in the middle under the arrow, and then I list out the elements in the middle. So we would put K, we would put Cl, and we would put O. Those are the three elements in the chemical reaction. Now what we're going to do is we're going to count the amount of each one on each side of the arrow. So on this side, we have our reactants. This side, we have our products. We're counting the reactant amount, and we're counting the product amount before we begin to try to balance. So over here on the reactant side, if you remember, since there's no subscript here, remember, when there's no subscript next to a symbol, that means it's an understood 1. So the chlorine also would be an understood 1, and then since we see a 3 subscript there for the oxygen, it's going to be a 3. Over here, once again, no subscripts for these guys, so they're 1s, and then we have a 2 here for the oxygen. So what we have to take a look at now is which elements are out of balance and where to begin. Well, the only one out of balance here happens to be oxygen. We have 3 atoms on the reactant side, we have 2 atoms on the product side. So they're not balanced, they're not following the law of conservation of matter. We need to fix that though. We need to conserve the matter. So what we can do in order to do that is we use coefficient numbers. And the coefficients are big numbers that you put in front of the entire compound. So in order to fix this though, we're going to have to use coefficients, and we're going to have to think. We have a 3 and a 2. Well, a 3 and a 2 means there's an odd number. The 3 is an odd number. So we have to kind of go with the least common multiple idea. The least common multiple between a 3 and a 2 is going to be 6. So I can multiply one of them by 3 and one of them by 2, and they both would end up having 6 atoms on each side. So this particular strategy, when you have an odd number like that, you might want to use the least common multiple idea. And that's what I'm going to do here. So in front of my oxygen right here, I'm going to put a coefficient, big number. That number happens to be a 3. So then I make the 3 up here times this 2. That now becomes a 6. So I have 6 oxygens on my product side. And then over here on the reactant side, in order to fix the oxygens, the only thing I can do is put a coefficient in front of the entire compound, the KClO3. I have to put the coefficient in front of the entire thing. And here, the oxygen has a 3, so I'm going to put a big 2 here. By doing that, my oxygens on my reactant side have also increased to a number of 6. But I did, by placing the 2 in front of the entire compound, alter the number of potassiums and the number of chlorines as well. So they're both changing. They have now changed to 2 for both of them. But this is actually an easy fix, because if I look from the reactant side to the product side, the KCl is together in a compound, and we can easily fix that change, where I went from 1 to 2, by, in front of the entire KCl compound, placing a 2. That makes this go to 2, makes the chlorines go to 2, and therefore now all the atoms have the same amount on either side of the arrow. So both the potassium and chlorines have 2 atoms on either side of the arrow, and the oxygens both have 6 atoms on either side of the arrow. So it's like a puzzle. You're trying to figure this out so that you have equal numbers of each type of atom. They don't have to be the same numbers, they just have to be equal numbers on both sides of the arrow for the balanced reaction. And that one, because there was an oddball, we would use the least common multiple idea and go from there. because example 2 strategy is just slightly different here. If you're looking at example 2, we're dealing with a different type of reaction. In example 2, we have, if you look here carefully, you will see we have calcium hydroxide, which happens to be a base. We have hydrochloric acid, and it says AQ next to it, so it tells us it's in solution. So we know that happens to be an acid. And then over here, CaCl2, which is calcium chloride, that is a salt. And our other product over here happens to be water. So if I'm looking at my components correctly, I can identify this particular reaction as neutralization, because we have a base plus an acid giving us water and a salt. So we would be able to identify this type of reaction as neutralization. Now, with neutralization reactions, if they're identified properly, you would need to use a specific strategy to help balance it more quickly. What we do here is we change the water to looking like this, HOH. By changing the water, it still has 2 hydrogens and 1 oxygen in it, but we're making them separate groups. We're making them an H group, and we're making them a hydroxide group, an OH group. And they're much easier to balance this way when you have the 2 separate groups to work with. Once again, we will construct a little table in the middle, like so. And we will put our groups there. So we have calcium, we have hydroxide, we have the hydrogen, and we have the chlorine. 4 different things. We're going to keep the hydroxides together as a group because now that I've changed my water, I've made it a hydroxide group on each side, and I can balance them by hydroxide groups, and it makes it a whole lot easier. So if I'm identifying the numbers here, looking up here, we have 1 calcium on the reactant side. We have 2 hydroxides because there's a little 2 outside the parentheses. We have 1, because they're understood 1s here, and 1 of the chlorine. 1 hydrogen, 1 chlorine in the hydrochloric acid. Over here, we have an understood 1 calcium. We have 2 chlorines. We have 1 hydrogen, and since there's no parentheses around the hydroxide, we're understanding it's 1 hydroxide as well. So now that we're looking at this, we can see that our chlorines and our hydroxides are out of balance. So it doesn't really matter which one we start with. We should probably start with chlorines maybe. I don't know, the oxygens and hydrogens usually work themselves out if you start with the other elements. So we're going to start there. Let's go ahead and balance our chlorines. So here I have 2, here I have 1. So on this side, I'm going to put a 2 in front of the hydrochloric acid. That's going to make my hydrogens go to 2 and my chlorines go to 2. So I have now fixed the chlorines. I have now made the hydrogens go up to 2. The hydroxides are also out of balance. Those are 2. But if you look conveniently, the hydrogens and the hydroxides are together over here in the same compound. So all we would have to do now is put a 2 in front of this entire thing. So we get 2 hydrogens, 2 hydroxides. And if you see here, then looking at the numbers, everything else is balanced. We have 1 calcium on both sides, 2 hydroxides on both sides, 2 hydrogens on both sides, and 2 chlorines on both sides. Everybody's balanced. We're not breaking the law of conservation of matter, and it is good to go. So that is the particular strategy you use when you're dealing with neutralization. Change the water to HOH. Now for example 3. You need to recognize that this is what type of reaction? It happens to be a combustion reaction. We have a carbon compound, hydrocarbon plus oxygen, giving us carbon dioxide and water. So we need to look at here and approach this one differently. This is actually, because it's a hydrocarbon, combining with the oxygen and not a metal. This one's going to be organic combustion. Organic combustion. So, this particular case, we're going to do something different. We are going to use the table, and we're going to arrange them in order of C, then H, then O. We call it the CHO. So balance the C's first, then the H's, and lastly the O's. And there's a little trick to this, because sometimes you get an odd number, and then at the end you do this little trick and it makes it work quickly. So, setting up our table, we only have 3 elements to contend with here. We have C, then H, then O. On this side, we have 6 carbons, 6 hydrogens, and 2 oxygens. On the product side, we have 1 carbon here, 2 hydrogens over here, and now we have to add up the oxygens. There's 2 in the carbon dioxide and 1 over here in the water, so that's a total of 3. So, now looking up here, we have a bunch of stuff out of balance, so that's why we go in order. We're going to do the carbons first. So let's go ahead and balance out our carbons. In order to make them have 6, we put a 6 here. So that changes my carbons to 6. I'm not even going to bother to add up the O's yet. We're going to do that at the very end. Then we're going to balance the H's. We have 6 on the reactant side. We have 2 on the product side. We need to have them be equal, so I'm going to multiply it by 3, because 3 times 2 will give me 6. So put a 3 there, that makes my hydrogens go to 6. At this point is when you need to add up your oxygens on the products side. So if I'm looking here at my carbon dioxide, 6 times the 2, that's going to give me 12 oxygens. Then 3 times the 1 here for the water is going to give me 3 oxygens, which is a total of 15. So we're going to change this to 15. Now 15 is an odd number and very hard to balance with. So this is where the trick comes into play, and you have to pay attention. Over on the reactant side, our oxygen is by itself. It's O2. So everything pretty much is going to be divided by 2 here. So if I take, because everything that I would put in front of the 2 is going to be multiplied by that subscript of 2. The best way to do this is to take the 15 and divide it by 2. Well, that gives me 7.5. 7.5 is not a whole number, and coefficients we know are supposed to be whole numbers. Well, I'm going to do this little trick here where we're going to put the 7.5 right now in front of the oxygen. We're going to leave it there just for one moment. 7.5 can't be a coefficient because it's not a whole number. So the best way to do this now is to get rid of that 0.5, just like we did with the empirical and molecular formula sheets. When we got 0.5s, we did what with our 0.5s? We multiplied them by 2. But what we did to 1, we had to do to everything. Couldn't just multiply the 1 by 2. We had to multiply all of the elements by 2. So that's what we're going to do here as well. We're going to multiply the entire coefficient system by 2. So since there's no coefficient here in front of the C6H6, the benzene here, we're going to multiply the 1 by 2 and make this a 2. We're going to take the 7.5, we're going to multiply that by 2 and get 15. We're going to take our 6 here and multiply it by 2 and get 12. And we're going to take that 3 and multiply it by 2 and we're going to get 6. So our final coefficients for this combustion reaction, 2 for the benzene, the C6H6, 15 for the oxygen, the O2, 12 for the carbon dioxide, CO2, and 6 for the water. So that's the little trick at the end. If you get an odd number, you need to multiply everybody by 2 at the end. If you got an even number for your oxygen, then you could stop. You could just divide that number by 2 and stick it in front of the O2. You wouldn't have to multiply everything out. Some of them work out to be even, where you just divide it by 2 and put that number in front of the O2. Some of them come out odd, if they do come out with a 0.5 like this, where you divide by 2 and you get a 0.5. You have to do that added extra step at the end and multiply every coefficient in the reaction by 2. Combustions are pretty much the most difficult ones to balance, so do pay attention, go back over this if needed. Now for example 4. Example 4 is showing one where we have lots of polyatomic ions in it. And if you have polyatomic ions, and they're on both sides of the reaction, you can keep them together as a group. You don't have to separate them. It makes it a whole lot easier when you're balancing chemical reactions. So we're going to set up our chart just like before. There should be 4 different groups if I'm looking correctly. Oh, and by the way, yes, on this one, unfortunately, there was a typo, so you need to correct this before you begin. Change this to ZN3 parentheses PO4 with a 2 outside. If you remember, zinc actually is a +2 for its charge. Phosphate, PO4, has a -3, so if we crisscross them correctly, the Zn should get a 3, the PO4 should get a 2. So you might have that typo on your paper. It was mess up there, so please correct that or it won't balance correctly and you'll have lots of trouble trying to balance it. So please make that correction before you begin. So now looking at our groups, we have Zn, we have NO3 nitrate, we have Na, and we have PO4. So we have zinc, we have nitrate, we have sodium, and PO4. If you look on the reactant side, you have nitrate in the zinc compound, but on the product side, you have it as nitrate with the sodium. So they're on both sides. We get to keep them together as a group. We don't have to separate them. So now what we're going to do here, count again. We have 1 zinc, we have 2 nitrates, we have 3 sodiums, and 1 phosphate. Over here, we have 3 zincs, we have 2 phosphates, 1 sodium, and 1 nitrate. Lots of odd stuff going on there. So I'm going to go ahead by, first off, balancing the zinc, starting with the metals. That's a good place to start. So we'll go with the zinc here, starting at the top. And you'll see how it kind of evens and works itself out as we go. So if we start with the zinc, we would put a 3 here. 3 for the zinc. 3 times the 2 here now gives us 6 for our nitrates. So the nitrates went up to 6. Wow. Now, we can go ahead and fix those. Let's go ahead and take a moment to fix our nitrates, since we just changed them. Over here, I'm going to put a 6 in front of the entire compound to fix those nitrates. But now that makes my sodiums also go to 6, as well as my nitrates. So both of those are at 6. But now let's look. We need to have 6 sodiums and we need to have 2 phosphates. Well, actually works itself out nicely over here. We put a 2 here. 2 times the 3 will give us 6 for our sodiums. And 2 times the 1 phosphate, because there's no parentheses, it means there's only one of them. That means now we have 2. So if you look carefully, everything is now balanced. That means in front of this guy, there is no coefficient, and no coefficients means an understood 1. So really, it's just like a 1 in front of there. When there's no coefficient in front of it, it means it's an understood 1. Okay? So that's the basic gist of the different types you're going to see. This one has to do with polyatomics. If you have polyatomics on both sides of the equation, you want to keep those together as a group. Example 3 was a combustion where you did C first, then H, then O. Number 2 was a neutralization where you changed the water to an HOH. And then the first one was one where it just had an oddball and we went for the least common multiple idea. These are all in like the helpful hints. So you're going to do some practice now. Identify the type of reaction and write that on the line. And then show your work, set a full table, the reactants and the product side, and put the coefficients in front. Don't just do the table part. You actually have to write the coefficient in front of the compounds right here as you're going. Make sure that you're doing that as well. And complete the assignment as designated.